Now in this video, I've got the NPN 2 and 2222 transistor integrated circuit. And on the base of my transistor, I have the Arduino Nano microcontroller. The microcontroller will be inputting a square wave pulse that has a peak voltage of 4.6 volts. And my pulse also has a duty cycle of 50% and a pulse width of 100 milliseconds. Now this 100 milliseconds means that from here to here is 100 milliseconds, and from here to here is also 100 milliseconds. And I've got a 3.k ohm resistor, a 3.3k ohm resistor, and across the resistor is 4 volts, and across VBE is 0.6 volts. And on my collector side, I have the 1N4007 diode, and I've got a 10 millihenry inductor, and I've got a 100 microfarad capacitor in parallel with a 1k ohm resistor. Okay, so now what's going on here? The pulse will be going into the base, and the voltage will rise to a peak of 4.6 volts. 4 volts will flow across my resistor, and 0.6 volts will fall across my VBE. Now, as the pulse goes through my inductor, my 100 microfarad capacitor will charge up, and some current will also go through my 1k ohm resistor. So now, what voltage will my 100 microfarad capacitor be charged to? Okay, so you have to keep in mind that my pulse width equals 100 milliseconds. All right, so now I'm going to find my RC time constant. My RC time constant equals my 1k ohm resistor times 100 microfarads. And that equals 1k ohm times 100 microfarads. So now I've got an RC time constant of 100 milliseconds. All right, I'm going to go ahead and erase this real quick here. So my tau equals RC equals 100 milliseconds. Now what voltage am I talking about? My capacitor voltage equals 12 volts times 1 minus e to the minus t over my RC time constant, 100 milliseconds. All right? Now, I'm gonna take my 100 milliseconds and I'm gonna make that t. So I'm gonna go t equals 100 milliseconds. So now I have 12 volts times 0.632. That equals about 7.58 volts. Okay, so I'm going to be using 100 milliseconds as my T, and my output voltage will be 7.58 volts. Now, initially, that voltage will be right here across my 1 kilo. Now, when my input goes to 0 volts, my voltage will now be equals 12 volts times that will be e to the minus 1 because I'm still using 100 milliseconds. I'm gonna call it a 368 times 12 4.0 0.41 volts. Now that happens after my input goes to 0 volts for another 100 milliseconds. Okay. Now when my input is now at 0 volts, that is when my transistor turns off. Now when my transistor turns off, this voltage goes right here. And this is what the output looks like. I'll have a peak voltage of 7.58 volts and a bottom voltage of 0 volts. And my voltage across my 1K ohm resistor equals 4.41 volts. Now I have 12 volts. So across the front of my transistor, I must always have 12 volts. So if I have 7.58 volts here, I have to have 4.41 volts here. Or more precisely, 4.42 volts here. Okay, just to be perfect. All right. Now, this is what my output voltage will look like. Now, I call this an integrator circuit, right? Now, anytime you input a square wave into a charging capacitor, unless you let the capacitor charge up fully, you will always end up with an output that is either a triangle or sort of looks like one. This sort of looks like a triangle wave. It sort of. It's got the hump right here, see that, but it kind of looks like a triangular wave. Okay, that's what makes it an integrated circuit. And whenever I have 4.42 volts here, I will have 7.58 volts here. And this brings me to the end of the video. Subscribe, like, share. Subscribe, like, share. Thanks for your attention.